about, this will be a more tutorial talk, a longer one. So the topic will be combinatorial optimization, and in particular the use of Graver bases and proximity results for the solving integer linear program. So Fritz is a professor at EPFL in Lausanne, and he works in combinatorial optimization, so a field that is somehow loosely related to algorithm as we in algorithm design know it, but certainly very interesting with a lot of links. And recently there has been a large body of work on breakthrough algorithm using combinatorial discrete tools for solving quite a wide, broad range of ILPs in a very new way. And it can be said that Fritz was in the forefront of this batch of breakthrough results, and he will tell us more about what happened in this area in the recent years. So I'm very looking forward to the talk, so peace.
Thank you very much, Michal. That was a very kind introduction. Thank you very much. I would like to talk about, I was asked to talk about, can you hear me well, by the way?
Yes, very well. Yes,
okay.
Yes. It's
so I was asked to talk about integer linear programming, in particular methods for integer linear programming in block structure that lend themselves to augmentation, Graver bases, and so on. So my idea is to give you a selection of things that happened in the last years. And of course, this will be a selection which is a little bit close to my heart and also contains some of my results. And I have to apologize already to all these nice, to people who have done extremely nice things that I cannot mention in this 1 hour tutorial. But as Michal had said, there is exciting work from complexity theorists, in particular in the area of lower bounds based on the ETH. And I really like this work, and I will mention some of this as well. Okay, so I'll try to go into a full screen mode here. Oh, wait, sorry, this is not correct. Here we go. So, maybe we keep it like this, and then I zoom through the slides. All right. So here's what our protagonist is. This is integer programming. In integer programming, you are given a set of linear inequalities, and these linear inequalities, they define you a polyhedron. This is this pink area here. And you have a linear objective function, and the goal is to find an integer point in this polyhedron defined by the inequalities that maximizes this linear objective function. Now, this is an NP complete and versatile optimization problem. For example, we can model SAT, or we have many scheduling problems, the traveling salesman problem. The most efficient algorithm for the traveling salesman problem in practice are based on integer programming. Cryptography and many other fields use integer programming. Okay, so here's what I want to talk about. I will start by talking about integer programming problems with few constraints, and mention upper bounds and matching lower bounds, and the proximity theorem for integer programming with few constraints. And these results are based on the Steinitz theorem, that is a theorem from convex geometry. Then I will switch to integer programming problems in recursive block structure. This has received a lot of attention also in the field of exact algorithms, and in particular this n-fold setting and the bounded dual Trevis setting of integer programming. I will have a look at this in a slightly more general way, and the question will be which relaxation should we use, and what kind of proximity can we get for a certain almost obvious relaxation that could be used. Then I will spend some time on reviewing a technique of Norton, Plotkin, and Tardosh from 1992. And this technique is basically doing the following. Suppose that you have an optimization problem that you can solve very well, and now you add some constraints, right? Now, you can dualize these constraints and devise an algorithm for the Lagrangian dual. And this is very interesting for us as well, because for these integer linear programming problems in block structure, right, if we remove the linking constraints, then we have simple problems that can be solved even in parallel. And it turns out that this algorithm of Norton, Plotkin, and Tardosh can be used to solve these strong relaxations efficiently in near linear and strongly polynomial time, and what's perhaps more interesting, also in parallel. And then we come back to this setting of n-fold and beyond. So this is the plan of what I want to do. Good. So what's integer programming? We have mentioned it already. We have here this so-called inequality standard form. And we will focus in this talk on the equation standard form. This means that we have a set of equations, lower bounds, sometimes upper bounds, and x has to be in the integers. So now we suppose that, excuse me. Now we assume that we have few of these constraints. And when we have few of these constraints, there is a classical algorithm of Papadimitriou, which has the following running time. So if m is the number of, can you by the way see my hand here?
Yes, we do. Yeah,
okay,
yes.
good. So if m is the number of rows of the matrix A, and delta is an upper bound on the absolute values of the entries in A, then the algorithm of Papadimitriou runs in time m times delta to the O of m squared. So what I would like to start with here, because actually it's a very simple algorithm, is an algorithm by Robert Weismann and myself, and which was also nicely improved by Janssen and Rohwedder in 2018-2019. And this shows that such an integer program can be solved in time m times delta to the O of m. So compared to O of m squared, we lose a factor of m in the exponent. And I would like to mention that this has now a matching lower bound, which was provided by Knob, Pilipchuk, and Brogna in 2020. And interestingly, this matching lower bound even holds for 0-1 matrices. So for 0-1 matrices, you could just simply forget about the delta here, and you get a running time of m to the power of O of m, and the matching lower bound holds in this case. Good. So let me explain how to get this improvement from m times delta to the O of m squared to m times delta to the O of m, basically. So here we need the norm of b, but Janssen and Rohwedder got rid of this essentially because this can be replaced by the log. Okay. Let me first explain to you how Papadimitriou was solving this problem, and let me remind you that we don't have upper bounds. So what you can show with Hadamard bounds, with the Hadamard bound from a linear algebra, is that if there exists an optimal solution x star to such an integer program, then there exists one with infinity norm essentially bounded by m times delta to the m. So I want to remind you that delta is the largest absolute value of an entry of A. And now we can imagine that we are walking or we are completing step by step the optimal solution x star, and we are recording. You see here, this is x star 1 would be the first component, x star I would be the ith component, and we are recording the contribution that these x star give in terms of the vector when we multiply this with the matrix A. So in other words, A1 is the first component, the first column of A, AI is the ith column of A, and B prime would be the contribution of x star 1 until x star I for on the way to the right-hand side B, okay? And now, because we have x star infinity is roughly m times delta to the m, we can see that the infinity norm of this B prime is also roughly m times delta to the m. right? Because each entry in A is bounded by delta. But this means now, since we have m components in B prime, that the number of these B primes could go up to m times delta to the m squared. Okay. But now, if we have this information, we can write down a dynamic program. And this dynamic program is as follows. We have nodes, and in the first component of the node, we record the I here, so the largest variable that we've considered so far, and the 0, which is what in this first node, which is the contribution that we have reached on the way to B. And since we did not look at any variable yet, this is going to be 0. And now if we have looked at I variables, we have a contribution B prime. And now imagine, for example, that we say that x star I plus 1 is equal to 3, right? Then there should be an arc from I B prime to I plus 1 B prime plus 3 times the I plus first column of A. And we give this a weight of 3 times the cost Ci plus 1. Okay? And in this way, we can complete a dynamic program or directed graph. And what we have to do is we have to find the longest path from 0, 0 to NB. And this gives the running time of Papadimitro, which is m times delta to the O of m squared, because that's essentially the size of the graph. And we have an acyclic graph, and this means that we can compute the longest path in linear time. Okay, so this is this algorithm. Now, I would like to explain to you how we can compress this state space, right? So the state space of this dynamic program is essentially m times delta to the m squared. And how can we get rid of this? How can we compress this? Potentially losing some information. I'll come back to this later. But the key here is the so-called Steinitz lemma. And this is a lemma from convex geometry from 1913. Suppose that you have vectors x1 until xn, and n here is deliberately the number of variables of our integer program from before. And suppose that they have, and suppose that they are of norm at most 1, and they sum up to 0. Then we can rearrange these vectors, xi, such that each prefix sums. So we stop the sum at k, and will not be of norm at more than m. Okay, so here you see an example. Here we might walk out of the m ball quite a bit, but we can rearrange these vectors such that they fit in the m ball of the corresponding norm. Okay. Now, how can this be used in integer programming? Well, we can again have a look at the optimal solution. And this optimal solution gives us a Steinitz sequence, okay? And how does it do this? Well, again, A1 is the first component of A. We take x1 star times A1 and xn star times AN, and we subtract B. Now, this sums up to 0, right? So this is clear because it's a feasible solution. So what we can do is we can rearrange, and for now we assume that B is also of infinite norm at most delta. We can rearrange such that the partial sums of the columns never exceed 2 times m times delta in the infinity norm 2, because I'm removing B out of this picture. Okay. All right. So but then we can have a new state space. Okay. How many integer points are there whose infinity norm is bounded by 2 times m times delta? Well, it's 4 times m times delta plus 1 to the power of m. So this would be this cube here. Okay. And now in this cube, we link a vertex on integer point x with an integer point y if y minus x is a column of our matrix A. Okay, here you see this is a column of our matrix A, and we have also the cost Ci. Now in this state space, we have only m times delta to the O of m nodes. Before we had O of m squared. Okay. And this gives us the running time, because now we just simply have to look for a longest path from 0 to B. And this, so imagine here is B and here is 0. We have to look for a longest path from 0 to B. And this gives us an optimal solution to our integer program.
There is a question whether the Steinitz lemma is constructive of Yossi.
Oh, yes, it is. Yeah.
Yes, it is.
Okay, good. Now I want to explain. Oh, is there another question on this? Okay,
not
no.
that I see at this point.
Good. So now you see here we assumed that the right hand side B is also satisfying this norm of infinity norm at most delta, and yeah. By the way, so if in this graph we would have a positive cycle, then the integer program is unbounded, right? So this is also important to note. Good, because otherwise the longest path could not be computed. Good. So how can we get rid of this dependence on B? And here the idea is to as before we had B separate there, but now we say, well, suppose that the infinity, say the one norm of X star is K. Now we chop up our B in K portions, B over K, and we subtract it from A1, each copy of A1, each copy of A2, and so on, right? And this gives us our new Steinitz sequence. And here we can rearrange the columns now such that the partial sums of the columns have a distance at most 2 times m times delta from the line segment 0b. So this is a kind of this picture here. So we are smearing out this cube in the direction of B. And we know that there is a way to go from 0 to B within this sausage now of stacked up cubes. And we would have how many nodes? We would have essentially m times delta to the O of m times B nodes. And this is the running time, which is a little bit of a milder dependence on the norm of B. And here I would like to mention again that this is our result together with Robert, but Janssen and Robert have a very beautiful result where they show better constants here and also a dependence on the logarithm of B in this running time. Okay, good. So this was improvement in terms of dynamic programming for integer programming with a small number of constraints. And now the question is, can we do better? And the answer to this is essentially no. And I would like to mention this nice result here that provides a matching lower bound. So, so we suppose the ETH holds, so there exists no wait a minute. Okay, yes, there exists an epsilon larger than 0 such that 3 side cannot be solved in time 2 times epsilon times n. So if we assume this, then Knopp, Pilipchuk, and Bruckner in 2019 have shown that one cannot solve an integer programming problem for 0-1 matrices A even in time 2 to the little o of m times log m plus n is a number of variables. This is essentially the input length of well, and this B infinity is also small in their case. It can, by the way, always be reduced to the logarithm of B. Okay, so this means that the running time that we have is something like m to the m or m to the o of m, and there's nothing of the kind 2 to the little o of m times log m. Okay, so this is a wonderful matching lower bound. Are there questions?
Indeed. Any questions now? Please put them in the chat box.
Okay.
Yeah. So essentially, just to clarify that that we understand. So essentially, in the Papadimitri's algorithm, the state space was the full rectangle in a sense, right? And what you do, you reduce this whole space of states to the diagonal of this rectangle in a sense.
I'm not sure I understand which rectangle you mean. I mean, you have a bound on the yeah, the trouble. Yes. Well, I mean, we want to go from 0 to B, and we know that we can go there without diverting much from the line segment.
Yeah.
And in Papadimitriou, this was not clear.
Yes. So you essentially have the states only along the diagonal.
Yes. Good. Exactly. Okay. Now I understand your question. Yes, that's the point.
Good. Yeah. Good. We can continue, I guess. Yeah.
Good. So then I would like to mention proximity bounds. So what are proximity bounds and why are they useful? Proximity bounds measure the distance between an optimal solution to the linear programming relaxation and an optimal solution to the integer programming relaxation. For example, this classical theorem here of Cook et al. From 1986 says the following. So if you have an integer programming problem in inequality standard form, and X star is an optimal solution of the optimal vertex solution of the LP, then there exists an optimal integer solution Z star, which is of infinity norm at most bounded by the dimension squared times delta to the n. Okay, so their setting is a bit more, is a bit better because it's measuring in terms of the largest subdeterminant of the matrix A. But I've used the Hadamard bound and got rid of the subdeterminant and assumed the worst case for the subdeterminant to give this bound here. Now, in the setting where we have equation and few constraints, so M is the number of equations here, and we even now have upper and lower bounds, we can drastically improve upon the proximity theorem of Cook et al. Also with the Steinitz theorem. And this proximity bound says the following. Now again, let X star be an optimal solution of the LP relaxation. And then there exists an optimal solution Z star of the integer program here, which has now one norm. And see, this is a huge difference. One norm bounded away from X star by M times 2M delta plus 1 to the power of M. So why is this so interesting? Because you see here we have an infinity norm. Here we have an infinity norm. And here we have a one norm. And also in the bound on the one norm, the number of variables does not appear. Okay. So this means that that we can, for example, now use this to solve a 0-1 integer programming problem. Okay. So, okay, suppose that we have A, like in the setting of the lower bound that I mentioned before, A in 0-1 to the m by n, and X star is the LP optimum, okay? Then we can just say, well, we want to maximize C transpose times Z, where Z, and this is now a new variable, X star is no variable, right? So it's a constant, where, but you can see Z minus X star rounded down as a variable, where A times Z minus X star rounded down is equal to A times the fractional part of X star, right? So I just simply took the fractional part here on the other side. This is an integer. And now this Z minus X star rounded down is a variable that is in some components 0-1 and some components 0-1. And I know that the one norm is bounded by M to the O of M, okay? And then you can easily see that if you now do again the Papadimitriou style dynamic program, where we go from layer to layer, we have at most M to the O of M square stages, okay? But this is far away from the upper bound that I've mentioned before by Knoop et al. And here's my favorite open problem, or one of my favorite open problems. Is there, now let's take integer programming with few constraints and the matrix is 0-1, okay? So we have M rows, n columns, and the matrix is 0-1. Is there an M to the O of M algorithm for integer programming with upper, yeah, with 0-1 variables? Or in other words, more generally, is there an M times delta if we bound the components of A by delta? Is there an M times delta to the O of M algorithm for integer programming with upper bounds on the variables? So this is a very tantalizing open problem. Yeah, I would love to see progress on this. Good. Now, what are Graver bases? So we need to talk about Graver bases when we will talk about, because we will talk about block structured integer programming problems later, and so-called augmentation algorithms. Now, a Graver basis is a set of vectors in the kernel of a given matrix A. Okay, and suppose that, again, the infinity norm of A is bounded by delta. So an element in the kernel, integer element in the kernel, is an element of the Graver basis if there exists no other element in the kernel, which is non-zero, such that it is sign compatible with G, so that means Gi times Hi is greater or equal to 0 for each I, sign compatible, and it is smaller in absolute value. Okay, so that means the absolute value of Gi greater or equal to Hi for each I. Okay, so now let's take, for example, this matrix here. Yeah, maybe I switch to my iPad, then I can make some annotations.
So Yossi had a problem, had a question about the open problem.
Yes, Yossi.
Yes. So the question is why you cannot reduce the upper bounds to the unbounded case using slack variables.
Then we increase the number of constraints.
Yes.
Yeah. So then you blow up the number of constraints. Yeah. Very good.
Mm-hmm.
More questions. Let me use my iPad now, because then I can talk about Graver bases and annotate a little bit. Okay, so here we go. All right, so what's a Graver basis? A Graver basis element is an element out of the kernel, an integer element non-equal to 0, and there exists no other element from the kernel unequal to 0, which is sign compatible, and the absolute value of the components of Gi are greater or equal to the absolute value of the components of Hi. So, for example, let's look at this matrix here, and let's look at this element here from the kernel, right? You see we have -3, and 1, 1 added here. So this is really in the kernel, but it's not in the Graver basis, because what we could do is we could take, for example, 1, 0, and then what else would we need? So 1, 0 would be 1, 2. This would be -1, -2, 1, 0. You see is in the kernel. And it is sign compatible. It's sign compatible. And the absolute value condition is also holding. Okay. Now, it can be shown that the Graver basis, the one norm of an element of a Graver basis is rather small, and so the previous bound, for example, here mentioned by Shmuel in 2010 says the following: that the one norm of an element in the Graver basis also could also potentially depend on the number of variables. But with Steinitz, we of course get this upper bound here. And let me just tell you why this is true. So this would be M is the number of constraints, delta is the largest absolute value of a component of A, and we get 2M delta plus 1 to the power of M. And how do you show this? Well, if you look at an element in the kernel, then you have again a Steinitz sequence, and this time the Steinitz sequence are again columns of A. Okay, and we can arrange it such that such that no partial sum gets out of the box of side lengths M times delta. Okay. So how many integer points do we have in this box? Well, 2M delta plus 1 to the power of M. Okay. And now if we would have a Graver basis that corresponds here to a cycle, yeah, then this is exactly the cycle. We take it out, and it is an element that shows, it's also an element in the kernel, and it shows that it is actually not the Graver basis element that we're looking at. Okay. So you also get this upper bound here on the one norm of the Graver basis. And what is the algorithmic significance of Graver basis? Well, if you have a Z star that is feasible but not optimal, and Y star an optimal integer solution, then you see that A times Y star minus Z is equal to 0. And there must exist a Graver basis element, because this can be decomposed then into sums of Graver basis elements of this vector. there must exist a Graver basis element such that Z star plus G, so this G is feasible. And the objective function vector of C transpose times G is larger than 0. And this means that we can perform an augmenting step. And how can we find such an augmenting step? Well, essentially, again, by dynamic programming in a similar way as I showed you when we talked about integer programming with upper bounds, where we have a condition on the one norm. Then we can be sure that the state space in the Papadimitrio dynamic program does not explode too much. Okay, and interestingly, you get the same running time for integer programming as before. So this was, just to recall, m times delta to the O of m squared. You would also get it by augmentation.
So may I ask a question at this point?
Yeah.
So is it good to think about an analogy here to local search, where I am at a solution that is probably not, that's maybe not optimal, and now I would like to jump to another solution that is a bit better, and the Graver basis element is a basic step in local search for ILP.
Yes, or cycle canceling in network flows is another example. But it's local search, and you can always go into an improving direction. If there is no improving direction from the Graver basis, then you know that you're done. Okay. Okay.
If you have any questions, just put them in the chat box. I just remind all of you. Yeah.
Okay, good. So now, So now I would like to come to the final part of my talk, and in this I want to review this wonderful technique of Norton, Plotkin, and Tarbush, because it will come very handy, as you will see in a moment, to integer programming problems in block structure. Okay, and my idea here is to give you an intuition of this technique, and I hope that I can succeed to convince you that this is a very useful and very important technique for integer programming problems in block structure. Okay. So what am I talking about? So what's an integer or linear optimization problem in block structure? Well, it is something like this. I have so-called linking constraints. So here, those are the linking constraints. And if I remove these linking constraints, then my problem, my integer or my linear optimization problem, decomposes into n individual optimization problems. You see, if I would take these linking constraints away, then I only have to solve individual, without linking constraints. I have to solve just the individual problems. And they are maximize Ci transpose times Xi. Xi is an element of Qi. Okay, I didn't tell you what Qi is. So Qi here is a polyhedron. Okay, so think about linear programming. We have a linear program which is almost in block structure, but there are some constraints which tie these individual problems together. Okay, all right, and in the following, I will often talk about the linear relaxation of this problem and about this integer programming problem. And why is this an interesting why is this an interesting problem? Well, because we have seen in the literature recently many papers concerning so-called block structured integer programs. And one of them that has appeared quite a lot is the n-fold integer program. So what is an n-fold integer program? Here we have to maximize C transpose times X. And we have a constraint matrix of this form. Here are the linking constraints. And here on the diagonal are the block constraints that are individual. Okay. And there has been quite a lot of research giving algorithms for this. And it turns out that an n-fold integer program is fixed parameter tractable. Now I should say in which parameters. So here we say that we have R linking constraints, and here we say that we have S constraints in the BIs. Okay, so the AI are integer matrices in R by Ti, and the BI are integer matrices in S by Ti. Okay, now the number of papers that appeared in the last 20 years is quite substantial. I would like to mention the best running time that was obtained so far, namely the one by Janssen, Lasota, and Roberta in 2018. And they get something like this. So here's a parameter that, this is the dependence on the parameter. So this will be RS delta to the power of OR squared times S plus S squared. And this L here, so this L, I need to explain what this L here is. L is the maximum binary encoding length. And then we have something which is near linear. Okay, the rest here is near linear. Okay, what I should mention is that it's kind of easy to see that the proximity of the standard relaxation is has a lower bound of omega of n. Okay, this is for these n-fold IPs. And what do I mean by this? By this I mean you solve the linear programming relaxation by getting rid of the integer condition, and this gives you a vertex solution x star, and then within, even within infinity norm, at least n, you will not find the optimal solution, the optimal integer solution to this integer programming problem. Okay, so this is an interesting aspect of these block structured integer programs. Good. So what is it that I want to talk about? Right. So I mentioned this running time here already by Janssen, Lasota, and Roberta, and this is sequential running time. So it's near linear, but not strongly polynomial. We still have a factor of L squared in front of this running time, where L is the largest binary encoding. So what do I want to show to you now with this framework of Norton, Plotkin, and Tardosh? We can get a running time like this, and I take it apart for you so that you see what's going on. So if we look at the sequential running time, then we have something which is near linear, as it is above for Janssen, Lasota, and Roberta. But we do not have the quadratic dependence on the binary encoding length. So this is strongly polynomial and near linear. And we have a slightly worse parameter. In particular, what is slightly worse is here this 2 to the O of R times S squared. Otherwise, the parameters are the same. Okay? But perhaps what is even more interesting is that not all combinatorial optimization problems, or we don't know how to parallelize all combinatorial optimization problems, but this one we can, right? And this is tempting, right? If you just remove the linking constraints, then everything is parallel, right? So if we just remove these constraints here, then we can solve the problem in parallel on n parallel processes. So in fact, there is a way to save the ability to solve this problem in parallel, and I will explain this to you. And it is with the framework of Norton, Plotkin, and Tardosh, and with the algorithm of Megiddo, and I hope I will have enough time for this. What's the time now? Could you? It's still 15 minutes, okay?
Yeah, you have 15 minutes, but this includes also the questions roughly. But,
okay,
yeah.
Good. Good. So I will try to be quick, and this is a result of Jana Sloviacek, myself, and others that we recently found. Okay. All right. Good. So what is the summary of the ideas to solve such a block-structured integer program? If the qi are integral, okay, so this means that those are integer polyhedra, yeah, and we can assume that this is the case for n-fold because the qi's here would be, small dimensional, would be small dimensional as when n-fold. The qi would be xi such that bi times xi is equal to bi, and 0 is less than equal to xi is less than equal to some upper bound, okay? So this is, and we know how to solve these with dynamic programming, in fact. This is what I have shown you in the beginning. So this means that algorithmically, we have the integer hull of these in hand. With the integer hull, okay? And this I write like qii. This is the convex hull of the integer points in qi. Okay, so here are the ingredients. If the qi are integral and g is a bound on the L1 norm of the Graver basis elements of these qi's, then the IP-LP proximity becomes extremely small. And what does this mean? You see, I mean, here there is no dependence on the block length. There is no dependence on the variables. It only has R, which is the number of rows in the linking constraints, delta, which is the largest component of A, G, which is the largest one norm of a Graver basis element in the Qi, and then we have to the power of O of R. So this is a constant. This is really all you can hope for. And in addition, you know that most of the, if you go to a vertex solution, most of the xi's are integer. So this means if you are given such an optimal vertex solution to this relaxation, dynamic programming will find an optimal integer solution in the claimed time quite easily, right? Because it's just a constant away. Now the question is how to solve this relaxation. And this I want to explain to you. And we will do this with this framework that I mentioned, and we have to adapt it a little bit. And the rest of this talk is there to give you an intuitive description of what's going on. Okay.
So just to be on the same page. So from the proximity, you get that if you solve the relaxation, you will be very close to the solution. Yeah. Yes. And then you just make a short step from this relaxation, seeking in a small ball around this relaxation to find the best solution using DP. And you can do this even in parallel. There's an algorithm of Kotetsky where it builds it bottom up, and you can do this even in parallel. I will not mention this, but you can also do this in parallel. Okay. Yeah, and but the power is that we assume here that the QIs, they are the integer hulls. For example, you have bounds on the Graver basis norm for integer programs depending on the dual tree width, right? This you can plug here inside too, as soon as you know how to optimize over these problems. And the point is that the whole framework is hereditary, so we can apply it recursively. Okay, but let me explain to you now this Norton plotting and Tardo framework. Okay, good. So here we go. So this is what we have to do. We have to solve this maximization problem. Okay, so we have to maximize the sum I equal 1 until n ci xi, and remind you here xi is now a vector of variables. Okay, it's a vector of variables corresponding to the polytope qi. Okay, and we go here from I equal 1 until n. Good. Now the nice thing is, if we dualize, if we dualize these away, then we get the Lagrangian. Okay, the Lagrangian dual. If we multiply these constraints here with lambda, then L of lambda would be to maximize CIXI plus lambda times AIXI minus B divided by n. You see, I've divided my B up into the n parts. Okay,
So this is the Lagrangian. This is the Lagrangian for lambda. And in order to solve this, this relaxation, what I have to do is I have to find the optimum value lambda star, the value lambda star that minimizes the Lagrangian. And the Lagrangian here is a piecewise linear convex function. And what I need to do is I have to find this point here.
Why is it trivial that the optimum of the Lagrangian corresponds to the optimum, to the solution of the original problem?
It's not trivial, but you have to use linear programming duality.
I see.
You have to use linear programming duality, but this is the standard in the textbooks of linear programming and linear and convex optimization.
Yeah,
right? There is no gap because it's a linear problem.
I think there is a good intuition about it. If you look at this Lagrangian and you imagine its differentiable function, if you take the partial derivatives over lambda, then the maximization corresponds to the partial derivatives being 0, and the partial derivatives being 0 corresponds to the linear program being satisfied. So this is how you can see it.
That's correct. Yeah, I think that's correct. Good. So this is what we have to do. All right. But now the thing is that this Lagrangian here, this can be computed for lambda, for this one L lambda can be evaluated in parallel, right? Because the xi's here, they are not linked anymore. I've removed the linking constraints and I've put them in the objective function. Okay. Now I have to mention a technicality. I'm assuming that the optimization problem that appears in the Lagrangian, and it is a portion corresponding to the polytope Qi, is linear. And what do I mean by linear? By linear, I mean that the algorithm that solves this problem will not need the objective function vector explicitly. All that it does is it will query, it will launch linear queries on this objective function vector of this form. You see, here I have a query that D and beta come from the algorithm that solves this, and the algorithm just asks, is D transpose times the objective function vector currently less than or equal to beta? Now I can rewrite this as a linear query on lambda. Okay, so this is a query of the form A transpose times lambda is at most F. So this is a linear query on lambda. Okay, so again, I'm assuming that the individual optimization problem do not need the objective function explicitly. They only need to have answers to linear queries that they launch. Okay, and now here's the thing. Here is the heart of the idea of Plotkin, Norton, Plotkin, and Tardish. So suppose you can solve the restricted Lagrangian. And what do I mean by the restricted Lagrangian? By this, I mean this. I'm minimizing, now, before I had a lambda in R to the R, right? This was the usual Lagrangian. Minimize lambda in R to the R, L lambda. But now I'm not searching lambda in the complete space, but I search it in an affine space of dimension R minus 1. Okay, so this is an affine space of dimension R minus 1. And now suppose I have such an algorithm, then I can find the optimal lambda as follows. Okay. Look, what I do is I run the algorithm that evaluates L lambda, but I will answer all the queries as if they were for the optimum lambda star. Okay, how can I do this? How can I do this? I can do this with my algorithm that is solving the restricted Lagrangian. Okay, suppose, for example, there is this query here coming in. Okay, now let me explain to you how this works. So lambda star is the unknown optimal solution. So I have here my hyperplane, which is A1 transpose times lambda is equal to F1. Here I have the hyperplane A1 transpose times lambda is equal to F1 plus epsilon. And here I have the hyperplane A1 transpose times lambda is equal to F1 minus epsilon, okay? And now remember that the Lagrangian L lambda is convex, okay? And I need to decide, is lambda star on the right or on the left of this hyperplane, okay? So suppose epsilon is a very, very small value, okay? So think of it as infinitely small. Suppose that the shape of the L lambda, when I evaluate it here, is like this. Okay, so I'm finding the optimal solution on this restricted Lagrangian, on this restricted Lagrangian, on this restricted Lagrangian. So suppose it's going up. Then what do I know? I'm searching for the lambda that is minimal, right? So where is lambda? Is lambda star here or is lambda star here? Do you get it? Any answer?
I guess it's on the left.
Exactly. I'm happy that they're good students. Okay, good. Okay, but you see that with three calls to this algorithm here, to the restricted Lagrangian. Okay, I guess with three, I can make this decision. You know, where is my lambda star? Okay, so I can answer these queries and thereby deciding for lambda star, and then I will get my lambda star. Okay, so this is the typical thing that you have also in parametric search when you are, for example, designing a strongly polynomial time algorithm for finding a minimum cost to ratio cycle. It's a similar thing. You look at the queries and there's an if and there's a linear query, and then you go at the breakpoint and you decide whether I go left or whether I go right in the branching of the program. It's exactly the same thing.
It's as in binary search, let's say.
Yes, similar, but with parametric search. So you get rid of the dependence on the binary encoding. Okay, so now let's suppose that we have a running time for the restricted Lagrangian, and you remember this was for affine subspaces of dimension r-1, and t is the running time for L lambda. Then what is the running time that we get in the end for our algorithm that solves the Lagrangian? Well, it is t, the running time for L lambda, because this is an upper bound on the number of queries that I have to do. And for each query, I have to launch 3 times the algorithm on dimension r-1. Okay, and then you can go down in dimension. And what you see here is basically that you have an algorithm that runs in time t to the r+1. Okay, so this is not FPT. If r is the number of linking constraints. But there is one thing that you can do if things are in parallel, and that's the difference. Are there questions until here? I try to wrap up. Okay, I try to wrap up. Okay, so remember that in our case, these individual problems can be run in parallel. Okay, and they have a certain running time. Let's call this t max. Now, at each time step, there are queries, and we need to answer these queries for lambda star. Okay, I'm just doing the same argument as before. Lambda star is the optimum, and I'm assuming that I have an algorithm that solves me the restricted Lagrangian for dimension r-1. Well, but the interesting thing is this. With the parametric search technique of Megiddo, we can now take all these queries and condense them in very few queries for lambda, or very few queries for lambda star. Namely, the algorithm of Megiddo, and I'm skipping the details here, has a running time of 2 to the O of R times the logarithm of n operations on n processors. It's parallel. And the total number of queries for lambda star is negligible if you look at the dependence on the dimension. Previously, it was if you look at the dependence on n, not the dimension, right? So here you see we had omega of n in the running time because we had to stack up these individual problems when we run them sequentially. But when we don't run them sequentially, we have an extreme saving in terms of queries for lambda star at each time step, and we have at most T max, and this T max is the maximum time that we have for the individual problems. Okay, good. And let me just mention the result. So now it becomes FPT. So if we are parallel, then it becomes FPT. So this is the suppose that each individual optimization problem requires T max, then we have 2 to the O of R squared times T max times log n to the R plus 1 on each processor. Okay. And now what this means for n-fold, I don't want to repeat it. I've talked about the running times before. I think I'm running out of time, and I have to stop. I would just say that with this scheme, I think it's a really we need to master this in the field of block structured integer programming, because this seems to be a very good way to solve these problems that decompose into individual ones once you take away the linking constraints. So also for the so-called case of integer programming of bounded dual treewidths, there we have a good bound on the Graver basis norm, which enables us to use proximity. And with this scheme, we also get something which is near linear in n and strongly polynomial. And it has roughly these kind of this dependence on the parameter. Okay, can I stop with an open problem? Okay, so here's my open problem, and this is the following. So can you solve, the standard LP relaxation of n-fold be solved in O of n without any logarithmic factors, okay, times a parameter. Okay, so we still have some logarithmic factors, but I think this shouldn't be there. Okay, and this is a tantalizing open problem.
Do you allow delta there in the function f? No.
It's irrelevant because
it should.
It should be strongly polynomial, and yeah, so it should be strongly polynomial. It's just a standard LP relaxation where we don't replace the polyhedra by the integer halves. Okay.
Okay, so thanks a lot for the talk. We now have some minutes for the questions. So please, if you have any questions, ask. Yes, there is a question, first one. Is L of lambda piecewise convex? If so, does piecewise pose any problem in the algorithm for solving Lagrangian?
Yes, it's piecewise linear. It's piecewise linear and convex. Okay. And it does not, well, you can solve the Lagrangian, of course, also with the ellipsoid method in polynomial time, right? Because you have to minimize a piecewise linear convex function, and it's quite easy to see that you have it algorithmically under control. You can separate over the epigraph of this piecewise linear convex function by solving the individual problems, for example. So no, this does not pose a problem in finding the optimal solution. And the scheme here is just an efficient scheme if the problem that you get by dualizing the linking constraints becomes highly parallel.
But I think that the question also involved, does piecewise pose any problem? So do you need to do anything more technical at the point where the two segments link together?
No.
Okay.
You would replace by subgradients, right? So you would you can convince yourself of optimality by giving a correct subgradient.
Okay. Are there any more questions?
Thank you very much.
So maybe I can also ask a question, if I still may.
Of course, yeah.
Yeah. So can you name some examples of problems that you can for the algorithm community of problems that you can solve using enfolds, for instance, or this kind of block structured IPs?
Yeah. So there are scheduling problems, approximation schemes for scheduling problems, and efficient approximation schemes for scheduling problems. If some of the, well, each time when you are interested in parameterized complexity, there are many scheduling problems that then translate into an enfold optimization problem. I don't have one in my hand right now, but it is used a lot in the approximation community.
Mm-hmm. Okay, so if we don't have any more questions, then let's thank Fritz again for the talk. And we now have a break, right? Until 2, is it correct?
2:30, yeah. So
2:30.
We meet again for 2:30 for 2 talks and the business meeting. So please come.
Yeah, okay. So thanks a lot. And yeah.
Thank you.
Stay tuned. Yeah.
Thank you.